So thank you for inviting me, DK, and I'll talk about the performance engineering using MVAPICH and TAU. So first of all, I would like to thank the team, the MVAPICH2 team at the Ohio State University, as well as the TAU team at the University of Oregon for the works. The outline of my talk is I'll introduce the problem, I'll describe briefly the MPI tools interface and what is required to interface MVAPICH2 with TAU and what kind of problems we are trying to solve. And briefly, if there's time, I'll show you a quick demo of using TAU. So the broad challenge for the MVAPICH2 team is that can we design dynamic and adaptive point-to-point communication mechanisms that can deliver the best communication performance with overlap of computation and communication and the best memory footprint? And how can performance evaluation tools help in this broad challenge? How can we contribute and make a bridge between performance evaluation tools and the runtime system and exchange information in a way that can help this? So some of you may already know about TAU. It's a project which aims to provide performance instrumentation, measurement, and analysis technology on a broad set of HPC platforms. Our goal is to target all the languages, compilers, runtime systems, and HPC platforms. It has a widely ported performance profiling and tracing system. And we also have support for performance data management and data mining. We have a performance database. All of these tools are open source. We distribute TAU in a BSD style license. And its key distinguishing factor is that it can easily integrate with application frameworks written in a variety of different languages, whether your application uses Python with CUDA or Python with Fortran or C++ with MPI, with OpenMP and pthreads. TAU can handle many different execution environments and scenarios and help you evaluate the performance of your application. It can show you how you can improve the performance by focusing on code regions in your code and showing you where it spent its time and other execution resources. These are some of the things it can show you. For example, how much time is spent in key code regions at the loops, statements, and the routines. You can even look at hardware performance counter data using tools such as PAPI that can show you level 1, level 2 data cache misses at the level of loops. You can evaluate the memory usage of your code, when and where memory gets allocated, deallocated, if there are leaks. You can look at the I/O of your code, I/O characteristics such as which files are accessed, what is the bandwidth, what is the total volume of I/O, along which calling paths. You can see the contribution of each phase of your program and see the contribution of, say, I/O or MPI operations with respect to different phases. You can see how the application scales, what is the efficiency, runtime breakdown. You can also see how TAU can help you tune MPI for better performance. You can observe, control, and performance variables that are exported by MPI, in particular MVAPICH2, and generate a variety of different performance metrics that are represented in profiles and traces. Well, profiles come in many different flavors depending on what you choose to instrument and how you configure the measurement system. Excuse me. At one end, you have a flat profile that can show you the total contribution of different code regions in your program. You can generate loop profile, a call path profile. You can even do call site profiling in TAU. At the other extreme, you have tracing, and you can generate traces in TAU's native format that can be converted into like JumpShot, a tool that we ship with TAU, or you can also export TAU traces to OTF2 format and generate them natively in TAU now and launch Vampire to look at those traces. But the key point is, how do you instrument your code? And we have support for both direct instrumentation via probes, where you instrument a function with start and stop calls. And this allows you fine-grained control and accurate performance measurements. On the other hand, we also have support for sampling. This is indirect. You get a periodic interrupt from the system. This interrupt can be generated by either a timer, or you can use a hardware performance counter. And in that case, it's fairly straightforward. For example, if your application runs for say 100 seconds, and if your interval is say 1 second, you collect 100 samples, and a code region in say a function foo accumulates 30 samples, then you could say that roughly 30% of the time or 30 seconds are spent in this code location in foo. But you can do more advanced things there. You can finally control the period of interrupts. You can control which hardware performance counter is used to generate those interrupts. You can also sample the full call stack and unwind the calling stack when you receive a sample. And you can use these both approaches together. So you can see the instrumentation that can be inserted in the code, as well as you can generate samples. So once you have the performance measurement infrastructure in place, you can interface it with MVAPICH using a new bridge, or what we call the MPI tools interface, and allow these libraries like MVAPICH2 to be more configurable at runtime using the performance feedback that is provided. So MPI tools interface comes from the MPI standard, and it has been around for a while, but tools are slowly looking at this interface and adding more features in terms of support. The tools interface provides a very interesting platform for runtime developers and tool developers to collaborate and exchange information. Tools can provide performance data. It can extract performance variables that are exported by the MPI runtime, and then create automatic tuning plugins that allow us to go ahead and reconfigure the MPI runtime and generate more optimized executions. So with MPI tools support, there are two types of variables that are exported. One is the performance variables, or CVARS as we call them, and we have support for the control variables in MVAPICH. Some of these are listed over here. So you can see that for memory usage, you can see the current level of memory usage, the maximum watermark. In InfiniBand network, you can see the number of control packets, out of order packets. In point-to-point messages, you can see unexpected queue lengths. You can see unexpected match attempts, receive queues, how long they are. So registration cache, shared memory, collective operations, they all have very interesting variables. Things that until now were not accessible to performance evaluation tools. This information was retained inside the runtime, but with this interface of performance variables through this bridge, as we call it, the MPI tools interface, now they can export this data in a way that can be accessed very easily by any performance evaluation tool. So this allows us to look at all of these different constituents of the runtime and then do the integration. This integration is achieved, as I mentioned, with this MPI tools interface, where in this instance we are looking at TAU and MVAPICH as the two tools that use the MPI tools interface, where we can observe the performance variables and then effect change using the control variables. Now you may have seen that many MPI implementations provide a list of configurable environment variables. Okay, there may be like hundreds of these variables that you can change. But note that when you set an environment variable, it typically is set for all the ranks in MPI, and it's set before MPI init at program startup and remains static during the execution. With control variables, you can change that for each rank. You can change it for different code regions. So if you have an application that has different performance characteristics during the execution, you could potentially set it at different points for different phases of the application. You can also, in the case of TAU, publish this at runtime and have other tools like our beacon infrastructure for looking at the performance of the application at runtime and publish it in a graphical user interface. So you could monitor the execution of the code as it is running and evaluate memory levels and other performance variables. So what we have done in TAU is we have created a plugin infrastructure so that you can instantiate different performance tool plugins. And these are activated at runtime, and you can use this plugin architecture to tap into different salient events that take place in the program that are shown by the different boxes over here. So your plugin can describe what kind of events it's looking for and set the callbacks, and then TAU will call those callbacks routines. And we have created a auto-tuning plugin based on this infrastructure where we generate recommendations for the user and export them in the profile files. So you could look at the performance of the application as it executes and then load the paraprof browser, and it will have recommendations for you on what it thinks your application could do to get better performance. So here are some examples of using the MPI tools interface control variables to control the message size to which inline transmission of data is supported. You can control the size of the memory allocated by the MPI runtime in the VBUF pools, and you can control the number of those, and you can also change, for instance, the point at which you can use different protocols. So you can switch between eager and rendezvous protocols and specify the message size where this switch happens. So for example, if the limit was say 60 kilobytes and your application was using say 64 kilobytes and it was in fact using rendezvous protocol, if you change that limit to say 65K, then it would use the eager protocol. And by looking at the sizes of messages during the execution and calculating the average message sizes, you can see where you might use this. Another instance is where some of the collective operations are executed in the hardware itself, like in the case of Mellanox, where some collective operations could be implemented using Sharp protocol. And based on MVAPICH's recommendation, you could suggest that turn on this feature in MVAPICH2 to use the hardware directly, the network fabric and the switches, to execute some of those collective operations. So what this requires is for you to insert the TAU library during the execution. And to do that, we have a tool called TAU-exec. Now the beauty of this is that you do not need to change anything in your application. You can run your code like this, MPI run np1024a.out, and to introduce the TAU infrastructure in your code, you can just say MPI run TAU-exec with some options a.out. And it will use the LD preload mechanism in TAU, and then you can enable sampling, code sampling, as well as insert the MPI library. And you can track I/O, you can look at the communication matrix, you can do a lot of different operations. And then finally you launch the paraprof 3D profile browser. Now when you use TAU with MVAPICH2 and enable the tracking of the performance variables, you can get a listing of all the variables that are available from the runtime. So this is the listing in paraprof's browser, and here are the control variables that are exposed by MVAPICH2. And you can use an environment variable to set the value of those variables. Like here we are enabling the tracking of performance variables using the environment variable, and here I can change the control variables at runtime and specify a list of those variables to be changed, and then their values that we assign to those variables. And here's the list of values. And then once you put tau in your path, you can just say tau exec a.out with those options, in this case MPIT, and then launch paraprof and view the results. Here is an example of the output of the VBUF usage without the CVARS and with the CVARS, and you can see the decrease in the memory usage as we dial down this. So what I want to basically say here is that there are many knobs that the runtime provides. The tools can be used to change the default settings of your MPI and modify its behavior, both at runtime or just at pre-execution time. And we can create a library of plugins that are able to track what is going on in your program and then effect those changes at runtime. Okay, here are examples that we have for use with or without the control variables, and you can see the difference in performance in these slides. And with that, I would just like to say that we have a very configurable measurement infrastructure, and this collaboration with the MVAPICH2 team has been very fruitful in effecting the integration of the performance tools with the runtime. Just having a standard which allows the cooperation is not sufficient. You need a very active collaboration between both the runtime and the tools community to use those interfaces and effect the change. So here is a list of the instrumentation, measurement, and analysis support provided by TAU. Essentially, you use TAU to insert hooks in your program, and I described the runtime preloading of TAU's DSO, but there are other ways to insert hooks too. You can insert hooks directly in the source code by parsing the source code and inserting instrumentation calls in a copy of the source code before it is compiled. And we have compiler scripts that help you do that. So instead of using MPICC, you could use say TAU-CC or TAU-F90 as scripts. And you can also specify a selective instrumentation or a filter file that can describe what events are tracked and how you can exclude or include code regions for instrumentation. Instead of using the parser and doing the instrumentation at the source level, you can also use the compiler to insert the hooks automatically in your code at the routine level, and you can use TAU to recompile the application using these compiler scripts. But the runtime preloading option is a very interesting option. It allows you to look at the performance of your application without modifying the binary. And so it's a very good first step to using the complete range of capabilities that TAU's measurement layer provides, including support for the MPI tools interface and inserting the plugins and the auto-tuning components into your execution. So this is how you run TAU without any, you run the application without TAU, and then you can say TAU exec a.out, and you can say TAU exec -T MPIT to enable the MPI tools interface a.out. You can also enable GPU tracking options for CUDA, for OpenCL, for OpenACC. We have new support in TAU for tracking OpenMP instrumentation as well, with the OpenMP standard with the TR6 that was released in November last year. You will see many compilers come up with support natively for TR6 this November. We are hoping to see multiple compilers get on board, but you can immediately substitute the OpenMP runtime with an OpenMP tools enabled runtime like this, and use it together with MPI. You can also use sampling to sample the execution and track memory leaks. And this is how you can insert instrumentation in your source code. To do that, you should use these compiler scripts and set a TAU makefile environment variable and switch the name of the compiler. So every time you configure TAU, it builds a configuration with an MPI and a makefile that has unique tags in its name. And you can choose one of those makefiles and then set it and then use make and override the compiler if you want to do source instrumentation. When you use TAU exec, you can also use those same tags that are there in the makefile, and it will just load the corresponding libtau.so shared object. And you can see which one is being loaded by this -s flag. Here is an example of looking at the impact of modifying the eager threshold using the MPI tools interface in an application called 3D Stencil that was written here at the Ohio Supercomputing Center. Excuse me. And here you can see that if you look at the red region in MPI and the green as the rest of the application code, we have a shot of the Vampire tool over here from TU Dresden in Germany, and you can see that there is less overlap and less useful work that's being done by the application on the left side, and then we changed the execution and modified the eager threshold for this 3D stencil, and then you can see that the total time reduced and there was more overlap and it used the resources more effectively. There are several environment variables that you can use with TAU, and you can see the list over here, such as tracking the communication matrix. You can specify call path profiling, tracing, or enable sampling in your code. You can specify multiple metrics. You can specify how the period of the event-based sampling is modified, memory debugging issues. You can also download TAU from our website over here. And this is the location of the Performance Research Laboratory at the University of Oregon. We have a very active program for visitors, and if you would like to come and spend a day or two with us, we can do a lot with your application and study it and work with you. So please get in touch with us. I would like to thank our sponsors for this work, the US Department of Energy, including the DOE national labs like Argonne, Oak Ridge, Sandia, Los Alamos, Livermore, through the ASC NNSA contracts, PNNL, CEA in France, Department of Defense. The PET program has been a big sponsor of the TAU project, the MOD office, HPCMP, the National Science Foundation, Intel, NASA, and our partners at the Ohio State University, Paratools, University of Tennessee, Knoxville, the developers of PAPI, TU Dresden, the developers of the Vampire tool, and Eugene Supercomputing Center, who have developed the Scorpi, Opari, and a range of other tools. So let me just take this time to show you a quick demo of this this paraprof, and show you that this is the default execution of the code, and you can see the time spent in MPI Vadal. You can see the time spent in various code regions, and the samples are collected. We can also see inside the libraries and see which functions are being called with no change to the application executable. This is all using the event-based sampling. But when we enable the other MPI tools interface and use a different eager threshold for this 3D stencil, you can see that the application runtime, as shown on just this node 0, was 25 seconds without any modifications, and then just using the MPI run TAU exec a.tau, we are able to get that cost down to 77% of the original or use the auto-tuning infrastructure in TAU to get it down further to 76.7% of the total execution time. And you can see the difference in inclusive or exclusive time. Here we can see the 3D visualization, which shows you how the application executes on all the different ranks, and see the bar plot for that. And look at the ranks and the functions and the exclusive time, and zoom in and look at every function for the execution. And here it says that in this particular function called compute on host, it's taking the samples, and you can see that on thread 51 it takes 7.9 seconds. So you can look at the profile and see the shape of the profile for every rank. You can look at the actual variables that are exported. The performance variables can be seen in the context event window, where you can look at the message size for reduce. You can look at all the MPI tools variables that are exported by MVAPICH2. And MVAPICH2 does a great job in the use of this MPI tools interface. Other MPI implementations have not really caught on and are not exporting as much information or using the control variables and the performance variables like MVAPICH2 team has done. So they have done a remarkable job of this, and it shows you how we can do the interfaces. And really, any tool can use this interface. It's not TAU specific, and that's the beauty of it, that they provide this information through the tools interface, and any tool can pick up this data and implement the auto-tuning policies like we have done in TAU. So with this, I would like to end this talk and take on any questions.